Module 3 Mastery Assignment by Leslie Oy. Topic 1. Sequences. So what are sequences? Well, sequences are a list of numbers whose domain is positive integers but sometimes can also include 0. Sequences can be defined with an explicit formula where you can directly compute for any term in the sequence, or a recursive formula, which requires the computation of all previous terms. So let's see what this looks like side by side with an example. So for our explicit formula, let's say we have the nth term being equal to n over n plus 1, while for our recursive formula, we have our first term being equal to 3 and then our nth term being equal to 5a sub n minus 1 minus 2 when n is greater than or equal to 2. Notice for the explicit formula, we can directly compute to find the nth term. However, for the recursive formula, we need to know previous terms for our computation. For our explicit formula, we could put 1 into our equation and get 1/2 for the first term, 2/3 for the second term, and 3/4 for the third term. Let's look at the recursive formula. So we're given the first term equal to 3. But notice when we are trying to find the next term when we plug in n equals 2, we will need the previous term, in this case when n equals 1, which we are given to be equal to 3. So now we can substitute 3 into our formula to get the second term, which is 12, and then do the same thing for the third term and so forth, and for the third term we will get 58. Sequences can also be infinite. This means that the terms do not end and continue forever. In particular, we'll focus on finding if the sequence approaches a certain value, which is called the limit, and this is how it's denoted. If the limit exists, then the sequence is convergent, otherwise the sequence is divergent. Here are some properties of limits we can use to help us evaluate certain sequences. Notice we can split the limit, as shown here, or we can draw out a constant from the limit, and we can even apply a power to the whole limit if the power is greater than 0, as well as the sequence being greater than 0. There are also some helpful theorems we can use when evaluating our limit. For instance, if the limit as n approaches infinity of the absolute value of a sequence equals 0, then the limit as n approaches infinity of the sequence itself is equal to 0 as well. Another helpful theorem we can use states that if the limit as n approaches infinity of a sequence equals the limit, and f of x is continuous at that limit, then the limit as n approaches infinity of the function of the sequence is equal to the function of L. We can use this if our sequence has a limit we can evaluate and then substitute that value into our function in order to determine the overall limit. We use the other theorem if our sequence is strictly negative or alternating. One last thing we need to know is what a factorial is. This symbol is read as n factorial and is commonly found in sequences and series. If n is a positive integer, then n factorial is equal to n times n minus 1 times n minus 2 and times n minus 3 and so forth. But don't forget that 0 factorial is equal to 1. So for instance, if we're given 10 factorial, that's going to be equal to 3,628,800. Now that we know these things, let's look at an example. Determine the convergence or divergence of the following sequence. If the sequence converges, find its limit. So we're going to apply the limit as n approaches infinity of our sequence as shown, and then rewrite this. So we're going to get the limit as n approaches infinity of n plus 1 times n plus 1 minus 1 factorial all over n factorial. And notice that this simplifies to the limit as n approaches infinity of n plus 1 times n factorial all over n factorial. So our n factorials cancel out, and all we're left with is the limit as n approaches infinity of n plus 1. And when we plug in infinity, we're just going to get infinity. This means the limit does not exist, so this sequence is divergent. And notice if we tried to find our terms, we're just going to get 2, 3, 4, 5, 6, and so forth. Notice that these numbers continue increasing and won't approach a certain value, which again reinforces the concept that this is a divergent sequence. Now that we know this, let's move on to a different topic. Topic 2. Power series. A power series is an infinite series involving a variable raised to the power of the index variable, which looks something like this, or more generally in the form like this. This is a power series centered at C. A power series can be used to approximate certain functions. We can even create power series that represent certain functions, and we do this by working backwards. Particularly, we can be given functions that resemble the form like this. So once we identify our first term and common ratio, we can create a power series. When dealing with power series, it is also helpful to know the ratio test. For any series, we're finding the limit as n approaches infinity of the absolute value of a sub n plus 1 all over a sub n. So if our limit is greater than 1 or is infinity, the series diverges. However, if the limit is less than 1, then the series converges absolutely. But if it's equal to 1, then no conclusion can be made. We performed the ratio test to help us find the radius and interval of convergence. The interval of convergence is the set of x values for which a power series will converge, and the radius of convergence is basically half of the interval of convergence. There are three different cases we could have for power series. One is the series only converges at its center, x equals c, so the radius is equal to 0 and there is no interval of convergence. The second case would be that the series converges absolutely for all x. This means our radius is infinity, and our interval is from negative infinity to positive infinity. And our third case is that the power series converges absolutely on a certain interval. This means our radius is a finite number and our interval is from a to b, depending on whether we include those endpoints. Now that we know these things, let's look at an example. Find the power series for the function given below and indicate the interval of convergence. So we're given f of x equal to 4 over 3x minus 2. Notice this looks similar to what we used to find the sum of a geometric series. So now we need to divide by negative 2 to make it look more like it. So now we have f of x equals negative 2 over 1 minus 3 halves x. So negative 2 is our first term and 3 halves x is our common ratio. Now we can make our power series, which looks like this. And now we can find our interval of convergence. Realize this looks just like a geometric series. In order for a geometric series to be convergent, the absolute value of r has to be less than 1. So we set up our inequality and solve for x. So eventually we will get the interval from negative 2/3 to 2/3. And if we were to find the radius, it would be 2/3.